Hey everyone, so today we're going to talk about sedimentary rocks and some of the formations and structures that they can make. So first of all, why are sedimentary rocks important? They only make up a tiny fraction of Earth's crust. Igneous rocks make up the majority of Earth's crust. However, sedimentary rocks make up about 75% of our surface rocks. Not only that, they contain a lot of really important resources like coal, natural gas, things like that. The other thing we're going to talk about today is that they contain a lot of the puzzle pieces that we can use to piece together Earth's geologic history. So we can look at the structures and the type of sedimentary rock in different regions, and we can figure out what sort of environment could have existed there in the past. We can also look at imprints of fossils or fossils themselves that are preserved in sedimentary rocks, and we can figure out what life used to look like on Earth a million or so years ago. So we're going to start by talking a little bit about some of the structures that can exist in sedimentary rock and how those structures are formed. So since the formation of clastic sedimentary rock, and remember those are the kinds of sedimentary rock formed from actual pieces of weathered sediment, involves the settling of those sediments, they tend to form in layers, and those layers can give us a lot of clues as to the type of environment that the rock used to exist in. These beds, which they're called, bedding is layers of sedimentary rock, can be millimeters thick or meters thick. Discontinuities in bedding can tell you information about the geologic history of the area as well. The first type of bedding we're going to talk about is graded bedding. So it forms in slow-moving water. So whenever we have water, there are a lot of different sizes of sediment that can be transported. We can have large pebbly sediment, we can have medium silt-sized sediment, and we can have tiny, tiny little particles that are transported in the water as well. And they're transported to varying degrees. Obviously, it's going to be harder to push along a big pebble than it is to transport a tiny little clay sediment in a stream or a river. So what usually happens is the biggest pebbles sink to the bottom first, or they're just rolled along the bottom. The medium-sized pebbles hit the bottom second, and then the finest pebbles, the little sediments, the little clay particles, usually settle last. And so when all of those layers eventually form a sedimentary rock, you tend to have the coarser sediments at the bottom and the finer grained sediments at the top. Some of the rocks that you can get from this kind of bedding are, of course, conglomerate. You can also have something called cross bedding. So cross bedding will form where there's air or water current as the sediment is depositing out. So what happens is there's one direction of wind, or typically wind or water, and the sediments are being deposited out as the wind is blowing. So as you can see from this really amazing diagram that I've drawn, we've got and we can assume this is wind, so these will be sand particles deposited by the wind. The wind is blowing towards the right, and as it blows, it's depositing the sand in these different hills. But notice how only on the right side of the hill are we seeing much of a bedding showing up. So this is what cross bedding will look like. Here's an example of what it will look like in an actual formation. So here's a sandstone formation with a whole bunch of cross bedding. And if you look at the different layers, there's a layer here, we can actually tell the direction that the wind was blowing when this particular formation was laid out. And maybe over time the wind changes direction. You can actually see that in the cross bedding layers. The next kind of bedding is a ripple mark. So ripple marks are wave-like structures that are solidified into the rock, and they indicate, again, the direction of wind or water currents. An asymmetric ripple mark is one that's kind of angled and tilted to the side, which is telling you that there was a current in one direction. Whereas symmetric ripple marks, which look like a nice little sinusoid, tell you that the water was going back and forth pretty evenly, kind of like the tide on a beach or waves on a beach washing in and out. So again, here are some pretty amazing diagrams made by me. Symmetric ripple marks are telling you that the current is going back and forth pretty evenly, whereas asymmetric ripple marks are telling you the current was going in pretty much one direction. Here's an example of ripple marks. This would be maybe siltstone, maybe sandstone, maybe it could even be some shale. Next up are mud cracks. Mud cracks are created when water, which is washed onto a shore pretty infrequently, dries out the mud. and so cracks will form. We'll see this regularly in a field that's just had a downpour, and then it really dries out quickly. The mud will typically crack apart. Now, if that mud eventually lithifies and turns into sedimentary rock, typically would become shale, then those cracks, those mud cracks, can be cooked in to the rock. So mud cracks will tell you, hey, this was once a very wet area that dried out very quickly. Finally, this isn't really a sedimentary structure, but it's something special that can only occur in sedimentary rocks, something called trace fossils. So a trace fossil isn't a fossil itself, but it's an indirect evidence of life, like a footprint or a track mark. So here's a footprint on the left, we've got a footprint on the right, a bigger footprint on the right. You can also have tail track marks, snail track marks, and any other imprint of an organism's body would be a trace fossil as well. So now we talked about different structures, we can talk about different sedimentary environments. By understanding where sediments get deposited and how, geologists can understand what caused the deposition of existing sedimentary rocks. And they can actually piece together the geologic history of that area. So there's three kind of environments we're going to talk about: a continental environment, a shoreline, and a marine environment. And those are all shown on this diagram here. And as we talk about these different environments, we're going to kind of brainstorm what sorts of sedimentary rocks you could find in these locations. First up are continental sedimentary environments. The first one is called a playa lake. They're usually in dry areas. These lakes will dry up completely. And so, just like we mentioned when we were talking about sedimentary structures, if we have a whole bunch of mud that dries up pretty quickly, it's going to form mud cracks. And that's a pretty key feature in sedimentary rocks that used to be a playa lake. If a lake like this contained dissolved minerals like sodium chloride or calcium sulfate, the types of sedimentary rocks that we could expect include things like halite or rock salt or rock gypsum. The other sedimentary structure, of course, that we're going to see in a location like this are mud cracks. Next up, streams and rivers, where we've got lots of streams and rivers. We can see them all the time. We've got running water flowing continuously in one direction through a region. This can obviously lead to erosion. We see a lot of erosion around streams and rivers that exist today. But we can also tell where a stream or river used to be based on the structures that are around. A couple of key definitions. A suspended load means sediments are transported through this stream or river and kept suspended above the bottom of the stream because they're small enough. A bed load are sediments that are too big to be transported along the stream without touching the bottom. So these are like typically bigger pebbles if you have just a little stream, and those sediments will be rolled along the bottom. Those are called a bed load. If a small stream flows really, really slowly, the bed load is probably going to be pretty small because the energy of that stream is pretty low. So it's not going to be able to transport really, really big rocks. So the bed load in a little stream is going to be pretty small particles. So the bottom of a little tiny stream, you're probably just going to have smaller particles. Whereas if you have a very fast moving stream or fast moving rapids, they're going to transport even decent sized pebbles pretty easily in the water itself. And so the bottom of a fast moving stream or the bottom of a rapid, you're not going to see any sand, you're not going to see any little pebbles, you're just going to see bigger rocks because everything else was able to be transported along with that fast moving stream. Some of the sedimentary rocks that you'll probably find in an environment that used to be a river or a stream include conglomerate, because maybe the bottom of that stream, which had some pebbles, eventually lithified and turned into a nice little chunk of conglomerate. Alluvial fans. When a stream or river empties out very, very suddenly, the sediment gets dumped all at once. So here's a picture of an alluvial fan. You can see the river heading towards this area that's very flat. So all of the sediment gets dumped at once in this fan-like shape. Here's a nice picture of a mini alluvial fan. So we've probably seen these at beaches and things like that. They can exist on the large scale too, of course. When an alluvial fan happens, when that river or stream dumps all of the sediment at once, The biggest particles, the biggest sediments are going to dump first, whereas the smaller ones can travel further. So you will have some graded bedding. You will have larger sediments up front, smaller sediments further on. The other types of sedimentary rocks you could find include conglomerates. You can get sandstones in certain regions. You could even get siltstones in certain regions as well. All of the classic sedimentary rocks. Glaciers are really interesting. They are big, giant accumulations of ice and snow. They grow when you've got frozen precipitation that doesn't melt, growing over time, compacting, and because of the pressure, because of gravity and all that ice that's accumulating, there's going to be a layer of liquid right at the base of the glacier between the ice and the ground, and that's going to allow some sliding of this glacier over the continent. Now, because this glacier is so massive and it slides over the ground, it's able to scrape the ground, so it actually carves out chunks in the ground, and it actually picks up rocks and carries them for very large distances before dumping them out again. So glaciers are capable of plucking rocks of any size, even gigantic boulders, carrying them for large distance and then unceremoniously dumping them down in a brand new location. They're kind of like sandpaper scraping the land underneath them. When the glaciers retreat eventually, they dump all of this poorly sorted sediment over the land. So you can get a lot of interesting features that exist because of glacial retreat. Some of these are called terminal moraines. Some of these are called eskers, drumlins, kames. These are all special names for different hill-like structures or ridge-like structures that exist when a glacier retreats. And there are actually some around us that you can see. You just didn't know they were from a glacier. Here's one of my favorite pictures from a glacier. This is called a glacial erratic. It's a giant boulder that was plucked up by a glacier a long time ago, deposited kilometers and kilometers probably from where it was found unceremoniously in the middle of a field. So that's a glacial erratic. If you found a really big rock in the middle of the field and it didn't match the rocks nearby, it's probably because a glacier put it there. The sediment that a glacier deposits is going to be really random, not sorted well, and not eroded because it's been just carried in this giant chunk of ice for many, many kilometers. You're probably going to get some clastic rocks existing in some of these glacial features, glacial structures, maybe even some breccia, some poorly sorted, glued together, lithified sedimentary rock. Here are some additional features. An esker is like a really, really long ridge. Drumlins are little tiny cute hills. And terminal moraine is a really long ridge that shows you where that glacier used to end. Next up, we've all seen pictures of these before. These are sand dunes. They are very well sorted because wind can't really carry big particles at all. It can just carry sand. That's about it. So dunes are very, very well sorted sediments. They're all made of sand, and when they lithify, they make, surprise, surprise, sandstone. Some of the interesting features that you can find if you're talking about dunes include cross-bedding, because remember, wind typically flows in one direction. So you can get some nice asymmetrical cross-bedding going on, which will tell you millions of years later what direction the wind was blowing back then. Now we're on to shoreline sedimentary environments. A delta, you've probably heard of deltas before. A delta exists when a river opens up into an ocean or a sea. The current, which existed in the river, stops pretty abruptly and all of the sediment again gets dumped. So here's a beautiful picture which is taken, it's a false color image, and it's of a Russian delta called Lena Delta. You probably are familiar with the Nile Delta, which is a very famous delta at the end of the Nile River, of course. Lots of humans tend to live near deltas, and that's because all that sediment gets dumped in one general area, which leads to very fertile land because a lot of nutrients for plants and crops are dumped there as well. Lagoons are the next shoreline environment. Lagoons are very still. There's not a lot of current. They're shallow bodies of water, and they're typically teeming with life. So you are not going to find a lot of ripple marks in a lagoon because everything is very still. But because of all the life that typically exists in lagoons, you will probably find some biochemical rocks. If that lagoon eventually evaporates, You might find some mud cracks. The bottom of the lagoon is probably going to be just mud, which would eventually turn into shale. So it's also a really great place to find fossils. If you've got life and you've got mud, and the possibility that life will be buried in the mud and captured between those layers of shale, you could have a really good source for looking for fossils. Some of the biochemical rocks that you could find in a lagoon include coal, which is made up of primarily plant matter, but you can also find other things like sometimes maybe some chalk or something like that. Also a good place to find trace fossils. Beaches and shorelines are the transition from marine to coastline environments. And because beaches have waves that come in and out and in and out, they're a great place to find symmetric ripple marks. Beaches, we know, are made up of sand, so when they lithify, they will turn into sandstone. That is a good indication that, hey, maybe it's a beach. You've got sandstone and you've got symmetric ripple marks. It's probably telling you that used to be a beach. Interestingly, when you're talking about a shoreline, you can have different regions. So beach, that's where all the sand is. That's what will eventually turn into sandstone. A little bit further out where the water's a bit calmer, you will get the finer grain sediment settling to the bottom. So that's more likely where you're going to find shale. Even further out, you get coral reefs. You get marine shelled organisms that would eventually turn into things like limestone or chalk or coquina. Just for reference, there's a nice little piece of limestone from our neck of the woods. Here's an itty bitty little piece of coquina. The other interesting thing to note is that limestone, shale, sandstone, these are all things in our area in Hamilton, Ontario, near the Niagara Escarpment. And that's because we used to be on a shoreline. Shallow marine environments. Now we're on to the marine sedimentary environments. Usually shallow marine environments are dominated by a lot of sea life. So in these sort of situations, you're going to get some biochemical sedimentary rock. You can still get things like siltstone, things like shale, so your fine-grained clastic sedimentary rocks, those fine little sediments settling onto the bottom. But you're also going to get limestone, you're going to get some chalk, maybe some coquina, just from all of those organisms that are getting crunched up and settled to the bottom eventually. Deep marine environments, you're only going to find pretty much shale, because those deep marine environments are just going to have the tiniest little sediments ever so slowly settling to the bottom and eventually forming shale. Here's an interesting little thought about how can we figure out what the water level used to be, or how the water level of a shallow marine environment used to change. Well, we can think about the different regions of a shallow marine environment. We've got the beach, which would eventually turn into sandstone. We've got further out into our marine environment, which would eventually turn into shale, because those finer sediments are able to settle when there's not as much of a current going back and forth all the time. And then even further out, where we have our coral reef, we can typically get limestone. Now, if we wait many years and look at many layers of sedimentary rock, we can actually tell when the shoreline has increased over time or decreased over time based on where's the sandstone, where's the siltstone, where's the shale, where's the limestone. So transgression is whenever we have an increasing shoreline over time. So as you can see in this image, the shoreline is increasing over time. So as we get to newer and newer layers of rock, which means closer to the surface, the rock, the sandstone, for example, gets further inland. Regression is when the shoreline is receding over time. So if we look at newer and newer layers of rock, let's say we just look at the sandstone is further out, telling you that the shoreline is decreasing over time. And that's it.